So from the tangent line to the tangent plane, it's a direct extension, right? Generalization. So it's the same idea when it comes to the maximum and minimum values, the maximum point and minimum point. So let's just quickly do that. A function f of xy has a local minimum here. I'm going to put the maximum case in the bracket. So the local minimum, put the line a little bit longer. So local minimum or local maximum. And then put it in the next one. So I'm putting everything in one sentence using the brackets because it's not really new. So it's a local minimum at the point AB. If every neighbor point is higher than this output, okay. So if f of xy is greater than or equal to f of AB, and in the maximum case is that f of xy is always the neighbor is always lower than the big. When the xy pair is near the point AB. And then in that case, we just call f of AB as the minimum value or the maximum value. The output value, the value f of AB is called the local minimum or maximum value. So this is an exact extension of the same concepts in Calc 1. Okay. So if you think about it, in Calc 1, we just say the function f of x has a local minimum if f of x is greater than or equal to f of a for all x value that's near a. Okay? So that's the exact same thing. Here we just replace the univariate x by a bivariate xy pair. Okay. The above is an extension of Calc 1. So basically here, instead of putting down the words, let's just look at the figure. So basically, for whatever function that you define like this, then when you identify a local minimum, it has to be lower than all the neighboring points, right? So for instance, you can say this point, this is the local minimum, right? Basically, we just need to realize that for the neighbor points, let's say in this region, okay, in this open interval, we see that okay, the outputs are all like right here. Okay, so they're all higher than the black point. So the black point is the local minimum, right? That's just from the definition of Calc 1. And similarly, this point is local minimum, right? And then it looks like okay, this point is looks like this point is the highest within a small neighborhood. Then that's the local max. So so that's Calc 1. But then in multivariate calculus, f of x, y, then we just need to worry about all the neighboring points were in the plane. Okay. So let's look at the example. So here we're going to do a few counter curves. So let's just keep in mind about definitions. Okay. So we have x, y plane. So we use a few counter curves to represent the function. So let's say we have the level 1 to be a line, f of x, y equals 1. This is the output level 1. So basically, this means on this point, on this line in the xy plane, all the output of the function f of xy is going to be 1, right? And then we have a counter like this. So this is the level f of xy equals -2, okay? And then we have one that's even more in the middle, which is f of xy equals -3. And then let me give the lowest point in the region. So we have a point right here. Wait, let me put it a little lower. Right here. So this is associating to the x value 3 and the y value 1. So let me put it in. Let me put the values in purple. So this is 1. This is a 3. And let me change the color of the point in red. And the function value here is f of xy equals -4. Okay. So here basically just within these two counters, the output gets lower and lower, right? So the most outer is -2. The inner one is -3. And we don't really have a curve in -4 because now there's only one point. And we can expect the function value just don't get lower because we don't really see a lower counter, right? So here for this point, we can now conclude that the local minimum of the function is this at this negative is at this point. So local minimum at 3, 1. So basically the pair here is 3, 1, right? In purple. And the local minimum value is -4. Okay. So that's when we talk about local minimum value is the output, which is -4 here. Does it make sense? Okay. So let me also draw a few counters. So you see, above the line, it's lower and lower outputs, right? So on the other side, we have a few counters as well. So we have f of xy equals 2. And we have another one that's higher in the middle. So this is f of xy equals 3. And finally, we do the same thing. So there's a red point, which is f of xy equals 4. Okay. So I'm gonna give you the coordinates of the points to be 8, 3. Okay. So this will give you another local extreme, which is local maximum. So let's continue with the remark. So you see in red we have the statements are kind of long, right? We say okay, the local maximum is attained at the point a is -3 in the case, and the local maximum value is at 4, right? So it's kind of a long sentence to state the conclusion. So here I would like to mention that in optimizations we usually care about the location at which we attain the extreme value. The extreme the extreme value itself may not be that critical. So we usually say that 3, 1. So the local minimum is the pair 3, 1. Okay. So the input pair is more important. Okay. And then here the local maximum is attained at A is -3. So we just say A is -3 is a local max. Okay. All right. Now, let's think about the gradient direction that we were talking about. So the gradient direction, we know at a point that's gonna tell you the direction along which your function value increases the fastest, right? But then what can you say about local maximum point right here? So if there exists a non-negative a non-zero vector at this point, then it tells you walk along that direction slightly, then your function value will increase, right? So if you were at a local maximum, that tells you you cannot really walk along a direction and increase the function value. So it tells you the gradient direction there must be a zero vector. Okay. Recall. So this is the thought process that you probably want to think through. Basically, at a local maximum, your gradient direction somehow has to be a zero vector. Okay? The gradient direction is the direction along which function f increases the fastest. Suppose that the AB pair is a local maximum. So just like the local maximum that we have in the figure above. So basically, we may have a counter with a level, let's say k minus 2. And then on the inner, we have an even higher counter, which is level k minus 1. But then at this point, we just have the highest output level to be, let's say, f of a equals to k. Okay. So basically, we have a highest point here. Okay. So by that logic we mentioned, so we cannot really walk along a certain direction and increase the functional value. That tells you that the gradient vector has to be a zero vector. Okay. By the understanding of the gradient f above, we can speculate that the gradient nabla f of AB at the point has to be the zero vector. And if you think about a local minimum, it's going to be the similar idea, right? So if you have a local minimum that tells you, okay, this point is the lowest among all the neighboring points. So you also know that if you go along the negative gradient direction, the functional value will decrease the fastest, right? So it tells you if your gradient is non-zero, then you can walk along the negative direction of that. And potentially decrease the function value. So that cannot really happen for a local minimum. So similar argument for the local minimum. Similar. basically it tells you, at these local extreme points, the gradient has to be very special. Theorem. Consider a function which has n variables in general. So let's say f of x1, x2, all the way up to xn. If this little f has local maximum or local minimum, at the point A1, A2, all the way up to AN for this tuple ordered pair. And all the partial derivatives del f del xi exists at the point then all these partial derivatives have to zero. Then del xi at the point A1, A2, all of the n has to be a zero for all indices I going from 1 all up to. And of course, when we say all the partial derivatives exist and they have real numbers, their values, then you have to have the gradient to be zero. Okay, that tells you every component of that gradient vector is zero. Okay. So equivalently, remark we can say equivalently. In this situation, nabla f at the point A1, A2 all up to AN, this has to be a zero vector. Okay. So basically, if you think about it, this is again like a generalization from a univariate case. Recall, in the case when n equals to 1, we have that if f achieves local max or min at x equals a, then we have to have a prime of a equals to 2. So that's what's called a horizontal tangent, right? But if you think about the concept of critical points in the univariate case, then it also includes the points at which the function is not differentiable. Okay, so that's exactly why we have the above theorem. So basically, it tells you if the function is differentiable, basically in other words, that all the partial derivatives exist, then the gradient vector has to be zero. Otherwise, you may have a point that's not really differentiable. Okay. So in the univariate case, it's the same thing. So we have two cases. One, the points at which the function is not differentiable, and case two, that we need to look at the points with horizontal tangents. Okay. So remark. For a barrier function f of xy having two variables. The theorem states that so basically we need two things. So we need the assumption that AB pair is a local max or min. And we also need to assume that the partial derivative exists, right? F sub x and f sub y at the point exists. So that both exist. Then, given both conditions, we can say that the gradient at the point has to be in the zero vector. So this is so this arrow is in one direction only. So it's from the right to the left. Okay. Wait, from the left to the right. So you cannot really reverse the direction of the arrow. So that's the point that we want to emphasize. However, if you are at a point that's having a zero gradient, this does not necessarily tell you anything about the point AB. So this does not guarantee that AB is a local extreme. Okay. So you cannot really conclude anything about the property of the point. And also, we realize that we need the function to be differentiable at the point in order for the theorem to be applied, right? So still, there could be a local extreme points that have non-differentiable partials. Okay, so when the partials does not exist, then that point AB still is possible to be a local extreme. Okay, so f sub x of AB or f sub y of AB is not defined. So in this case, it's not necessarily, it does not necessarily imply that AB is non-important. Okay. So it still may be important. Local X. Don't worry. So how do we interpret this theorem correctly? How to interpret the theorem? So basically, when we talk about the local extremes, we have to consider the two cases. One, the places at which the gradient equals to the zero vector, and two, the locations at which the function is not differentiable. Okay. So one, when the gradient at the point AB is indeed the zero vector, then that tells you the point AB might be a local extreme, local maximum. And two, when the partial derivative f sub x or f sub y does not exist, then AB still might be a local extreme. But finally, the last item, we can know for sure that if the gradient at the point exists, but does not equal to the zero vector, then we are sure that AB is not a local extreme point. Okay, so the third item is exactly what that theorem tells you. But then still, in order to calculate the local extreme point, we still need to worry about items 1 and 2. Okay. And these two kinds of points are called the critical points. So that's once again an extension from multivariable calculus. Okay, so definition: a point AB is a critical point if either the gradient at the point of the function is a zero vector, or if either f sub x or f sub y does not exist. It's not fine. So let me quickly write down the example that we're going to discuss on tomorrow's class. So basically, if we look at the function f of xy equals to y squared minus x squared. So this is a very important example that we have seen when we illustrate the figure, but this function is actually having a zero gradient at the origin, but not really a local extreme. Okay, the critical points include the points at which your gradient is zero vector, and the points at which your gradient does not exist. Right? So the partials may not exist for some variable. But now, if you look at this, this is actually a Coulombic function, so it's always differentiable, right? So it tells you we only care about those critical points that have zero gradient. Okay? So first, the critical point. So we just put f of x, f of y, we compute, and then we make them equal to 0. So f of x here is now so you see there's only one term in terms of x, so there's negative 2x. And f of y is 2y. So you notice that you have to fix them to be 0 in order for the gradient vector to be the 0 vector, right? That tells you what? It tells you x and y has to be 0 at the same time. So that tells you there's only one point in the domain. That's the critical point, which is the origin, right? But now, if you recall the graph, it's actually not giving you a nice minimum or maximum because so when we're trying to sketch it, let's say if you fix x to be 0, right, then you have a quadratic opening upwards. So basically we're sketching so z equals to y squared minus x squared. And here we have the x-axis, the z-axis, and y-axis. So when you fix x to be 0, you have y squared, right? So that's quadratic opening upwards, and the origin x0, y0, and z0. So that's the point that we look at, right? This is the lowest point along this trace, right? But now if you look at where you fix y to be 0, that's actually the xz trace. negative x squared, so that's projected as opening downwards, right? And then you fill out the rest of the figure. So basically, if you have z value to be positive, you have a hyperbola opening along the y direction. But then if you fix z to be a negative number, you will have hyperbola that's opening along the x direction. And so you get the idea. So the shape of this surface looks like a core saddle, and that's indeed the name of that black point at the origin. That's called the saddle point. So this is not a local max, nor a local min, right? So here, so let's also put the things down in words. So here, this critical point that gives you the z component, the output to be 0. This is not a local max, of course, because the trace is in purple and it's a private opening upwards, right? So you have a few neighbor points that's higher than this black point. Okay, so this is not a local maximum. And if you look at the other trace in red, okay, we have a parabola opening downwards, so the black point is the highest point here, so this is not a local minimum. Okay, so essentially, this is the critical point that's not giving you anything. So this is what's called a saddle point. Okay. But this tells you what? This tells you sometimes the critical point will not really give you a local extrema. Okay. So 0, 0 is a critical point that is neither local mean nor local max. It is called a saddle point. Any questions? All right, so now let's look at another example. Basically, now we have another bivariate function f of xy equals to 4 plus x minus 1 squared plus y minus 3 squared. So, well, if you look at this expression, you see, okay, x minus 1 squared, y minus 3 squared, they are all non-negative, right? So indeed, in this situation, you do have a minimum, which is the output of 4, right? Because you're adding the squared terms, and the squares could be zeros. So, but still, we need to be systematic. We look for the critical points. So here, the function is well differentiable. We have the partials at every pair of inputs, right? So we just look for the critical points that are that have critical points that have 0 gradient. Okay. So f of x, f of y. So f of x, if you do the partial derivative of x, you only have the second term in the sum to be the expression about x. So that's giving you 2x minus 1. The partial derivative is right y. That's only the third bracket. Well, the third term, which is the y minus 3 squared. That's involving y. So 2y minus 3. That's a derivative. And then you have to fix them to be zeros. And this gives you the system of variables of equations. So here 2x minus 1 equals 0, so x must be 1. And then y here in the second equation, you can deduce that it must be 3. Okay, so critical point, and through the argument that we gave at the beginning, we know this is indeed 1, 3 is a local minimum because f of 1, 3 just make the squares vanish, right? So it's 4 plus 0, which is a 4. And we also know that any xy pair gives f of xy. So let me cheat by copying the functional expression, but here I only want to give the argument that the squares that I have are non-negative. Okay, so this square is non-negative, this square is non-negative, so the whole sum is going to be greater than or equal to 4, which is the output at the point 1, 3. Okay, so this tells you what? This tells you not only the neighboring xy pairs are giving you larger outputs, but also for arbitrary xy pairs giving you a larger output than f of 1, 3. So this tells you, of course, 1, 3 is a local minimum, but then we can say even further that 1, 3 is an absolute minimum. Okay, so 1, 3 is a local minimum, and in fact, it is also a global minimum. Sometimes they call it also the absolute minimum. Right, but now if you think about these two examples, these are really special or even simple functions. So it's kind of a hard process if you just find the critical point and then try to identify whether this is the smallest output or the largest output among the neighborhood or not. So we have another test, okay, that's called the second derivative test. So that makes the process of finding local extreme point even more systematically. Okay. Second derivative test. So if you recall, in Calc, I think in Calc 1, what we do here is that, okay, you compute the critical points. So basically you compute the horizontal tangents. And then you compute the second derivative at the point. If it's a positive value at this local extreme point, well, at this critical point, then you have sort of a convex shape in your graph, right? Then you have a local minimum. And if your second derivative is negative, that tells you have a concave shape, right? But here we're also utilizing the second order partials, okay, for a critical point. Let's say AB with f sub x of AB equals to f sub y of AB to be 0. We want to we notice that we have 4 second order partial derivatives, right? So we want to put them together in a order 2 determinant. So we call it FD. So basically, you put in the order 2 determinant, so this is a 2 by 2 matrix that, well, that you put in the determinant form. So the way that you do it is you put f sub xx in the first row, first column, f sub xy in the first row, second column, f sub yx in the second row, first column, f sub yy in the second row, second column. Okay. So this is actually a scalar value that you can compute when you actually computed the all the other two partial derivative values. So of course, by definition, you know the calculation. So this is going to be the diagonal values multiplied minus the off diagonal values multiplied, right? So this equals to f sub xx at AB times f sub yy at AB minus. You also know that f sub xy and f sub yx, they eventually have to agree. So you can just put f sub xy of AB squared. So this is a critical quantity that you evaluate when you're doing the second derivative test. So let me put a box here. Okay. And now we notice that this is actually a bivariate case, so it's complicated. So there are 4 situations. There's 4 cases that we need to watch out for. Case 1. When cap D, when this determinant is negative, that gives you a conclusion that AB, the input pair, is a saddle point. I.e., it is neither local max nor local min. Case 2. When cap D is positive and f sub xx, this is what we call the principal minor. So basically this is actually the first row, first column value, okay? So the sign of this is important. So when this is positive, we can tell you, we can conclude that AB is giving you a local minimum. So you need both cap D and f sub xx to be positive, okay? So that gives you a local minimum. Case 3. So cap D is still positive, but the sign of the principal minor is negative. Okay, so f sub xx is a negative value. So now this tells you that AB is a local maximum. Okay. So now that takes care of 3 different cases where we have a local max, local min, or saddle point. Right? And now finally, case 4. If cap D is 0, then we cannot really conclude anything. Inconclusive. So this is the hard case. So basically, AB can be saddle point. Local max or local. So we cannot really tell what that point AB is. Okay. So within our course, we usually will get into the first 3 cases. Okay. The first 3 cases. So the fourth case, you see, Cap D is 0. So this is usually what's called a degenerate case. So this determinant is a 0. So let me move the things a little bit to the left, so it looks a little bit nice. Right, so that's the secondary test, very important. Okay, so this test will give you the conclusion whether the critical point here you're looking at is the local max or not, local mean or not. Okay, so here for proof, see the textbook. So usually when the proof is given in the textbook, then actually the result is somehow not so hard to comprehend. Okay? So let's look at an example. Let's say we have f of xy to be x to the 4 plus y to the 4 minus 4xy plus 1. Right? So this is definitely an example that is somehow hard in a sense that if you, well, it's not really practical to analyze the function and conclude whether you have a local max or local. Okay, so this is the situation where the test, the secondary test is handy. So we just do this systematically. So we need the critical points. Once again, this is a very nice function that is polynomial, right? So it tells you the partial derivatives are always existing, are always well defined. So we calculate all the points at which we have the zero gradients, and then we compute the Cap D and the principal minors at the critical points. Okay, so very systematic. So critical points. So that's the first step. F sub x, f sub y, we force them to be zeros, right? But then let's calculate. So we see, okay, we have 4 terms, x to the 4, y to the 4, negative 4xy plus 1. So the 1 doesn't give you anything when you differentiate. The first term and third term are involving with x, right? So that's 4x to the 3 power minus 4y. So 4xy gives you 4y. When you do the partial with y, you see only the second and third term are involving y, right? So that's 4y to the 3 minus 4x. Okay, so you're doing the partial with y. Okay, and now we set them to be zeros. So this is not even easy to solve the system. Okay, so here we can cancel out the 4s on the right hand side and left hand side. So we see that x to the 3 minus y must be 0. And in the second equation, we see that y to the 3 minus x must be 0. So in other words, y must be x cubed and x must be y cubed. Okay. And now we want to solve for the all the possible x values that satisfy the system. Well, but fortunately, well, x is y cubed, then the y is x cubed. So you can do a substitution to eliminate one of the variables. Hence, x must be, so let's eliminate y, right? X is y cubed from the second equation. But then we substitute the fact that y is x cubed from the first equation. So that's saying y must be x cubed, and if you do that substitution, then y has to be cubed. So the whole thing has to be cubed. Okay? So this indeed will give you a power function in terms of x. And here, what do you do to simplify this? So you have 3 in the exponent and in the outer exponent as well, right? So that tells you the exponents can be multiplied. Right? So that's 3 times 3 is 9. And then, well, we need to do some factorization. Okay, so we have x equals to x to the 9, right? If you subtract both sides by x, you will have x to the 9 minus x equals 0. And even you can factor it by stating as, yeah, let me write it down. So 0 equals to x to the 9 minus x, which equals to, you can factor x, you will get x to the 8 minus 1, right? So x to the 8 minus 1. So this is something, so I would say, in general, the factorization is not really required. And also, the fact here is that it's a high degree polynomial. Usually, it may not be easy to factor. But here, as a special case, this is not really difficult because x to the 8 is actually x to the 4 squared. So this is a difference of squares, that formula that you can apply. So this, let me just write down the final result, but it's not really. It's not a required factorization step. So this equals to x times, okay, x to the 8 minus 1 is actually x to the 4 plus 1 times x to the 4 minus 1, right? And then x to the 4 is also a square that can be even factored as x squared plus 1 times x squared minus 1. And x squared minus 1 is x plus 1 times x minus 1. So what's in the red bracket is not required, but you certainly want to know that there are 3 real solutions: 1, -1, and 0. Another way to think about it is that, okay, my x to the 8 must be 1 from here. It tells you if you take the square root, you have to have the positive square root, right? And then if you take the square root further, you will still have the positive square root because the expressions on the left-hand side, they are all non-negatives, right? So now x squared equals 1, that tells you x must be either +1 or -1. So this is another way to think about it. But either way, you have to do something reasonably to get the conclusion right here that x must be 0 or +or -1. And there are 3 solutions. Any questions so far? Yes.
Can you refresh me in terms of when it's, go back to where it's like x equals y to the third, and then it's somehow it's given to x to the third power. Can you explain to me how you get that?
Oh, that's the rule of substitution. So basically, so let me see. This is equation 1, this is equation 2. Let me label that in red. So in the next line, I wrote x equals to y cubed, right? That's actually equation 2. And now we utilize equation 1. So equation 1 is actually saying y must be x cubed. Right? So we want to put this into the equation 2 so that y is eliminated or substituted. Right? So here, this is equation 1 that we utilize to replace y by x cubed. So that's exactly this expression replaced with x cubed in the bracket.
Okay.
Yeah. This is actually a very good question. So the elimination is not really practical in this sense, but the substitution rule is also is practical here. And then we can multiply the exponents. Any other questions? Right, so now what do we do? So we have 3 possible x values, right? 0, 1, and -1. So these are the possible x values. So what about the critical point? What do we know about y? So here we want to look for the critical points as xy pairs, right? So now how do we determine the y value? yeah, we plug it back into, let's say, the equation one that we utilize, right? So y must be x cubed. So here we have three situations in terms of x, then we need to respectively calculate the y values. Okay, that's a very good observation here. Therefore, since y is x cubed, we have three critical points. So when x is 0, y is x cubed, which is 0. So when x is 1, y is 1 cubed, which is 1. When x is -1, y is -1 cubed, this is still -1. And so we have three critical points. Okay, so now we just need to study that determinant cap D in the second derivative test for all these 3 points. Okay? So now we just calculate the second order partials. We have, so we just do the calculation. So f sub xx. So f sub x is it's this equation right here. X 4x cubed minus 4y, right? So we just do the partial with respect to x, and gives you 12x squared. So that's f sub xx. And now f sub xy is, if you do the partial with respect to y, you'll get a -4, right? And you can expect that's the same thing if you do f sub yx. Because this function is actually so nice that the second order partials are also well defined. So f sub yx, if you do the partial for f sub y with respect to x, this still give you a name. If you just check the line right here. And then finally, you need f sub yy. If you do the partial with respect to y for the circle formula, that's 12y squared, right? And we are getting there. So we can just put the things in cap D. Okay? Cap D is the determinant of order 2 that you put the these second order derivatives, partial derivatives into the determinant. So that's actually 12x squared as f sub xx. And on the diagonal, you have 12y squared as f sub yy. Okay? And the off diagonal, you have f sub xy and f sub yx. Yeah, so here, let me put in the next step if. So this is after my substitution, right? So just recall the equation is f sub x, f sub xy in the first row, f sub yx and f sub y in the second row. And then just calculate, so this is giving you what? So basically you multiply the diagonal values, that's actually 12 times 12, that's 144, x squared, y squared. So diagonals multiplied minus the product of the off diagonal numbers. Okay? So that's actually 16. And we are almost done. So now, so this is the determinant value for any xy pair, right? But now we have 3 xy pairs. So we just calculate at 0, 0. What do we see? We see cap D is -16, which is negative. Okay. So if you refer to the cases, that's case 1. So cap D is negative, so it is a saddle point. So that's good. So we calculated the determinant cap D to be negative, right? So that's a saddle point. And now let's look at 1, 1. So here we have x and y to be 1. So if you plug in, you have 144 minus 16, right? That's 128. That's positive. Okay, so now, so that tells you, okay, we have to be in case 2 or case 3. So we still need to care about the value for f sub xx. Okay, so now we evaluate f sub xx at 1, 1. So that's actually what? That's actually 12, right? So x is 1. That's also positive. So what does it tell you from the secondary test? So local minimum. It is a local minimum. Okay. And finally, let's look at negative 1 pair. And you see that the conclusion should be the same, right? Because here, for everything that we calculate are in terms of x squared and y squared. So that's still the same value. So cap D is just 1.116 again, positive. And f sub xx, the principal minor is also 12, which is positive. So the same conclusion, right? So it is a local mean. So here we see that we have 3 critical points. One of them is center point, but the other 2 are both local minimum. Okay, so there's no local maximum. Any questions? Yes.
Can you go back to those 3 critical points? Did you plug it into the f sub x or f sub y, or like the equations of the equation 1 or equation 2?
Now we utilize equation 1.
Okay.
Yeah. So we want y, right? So from equation 1, we know y must be x cubed. So that's the equation that we utilize. So essentially, we use one of the equations to do the substitution in the next line, right? So that's the equation that we go back to.
Can you use both? Or just...
Well, so that's also a very good question. So if you look at these, right? So equation 1 is saying y must be x cubed. Equation 2 is saying what? Equation 2 is saying x must be y cubed, or y must be x to the 1/3. So it still works, but it's not as straightforward.
Okay.
Yeah, so I would say equation 1 is a little bit more straightforward because you don't have to solve. Right. So here, once again, we are given the x value now at this step. X must be plus or minus 1 or 0, right? But still, we want the y value. So directly from equation 1, we know, okay, y must be x cubed. So that's the more straightforward way. Or if you say equation 2, that tells you, okay, y must be x to the 1/3, taking the third root. So the conclusion is the same, that y must be 0, 1, or -1 respectively. Then there's a root. That's the only difference. All right. Any other questions? So this is a very, very, very important example. Okay, so now let's look at another example, which is a little bit more physical, I would say. It's a application. So basically, we're talking about a rectangular box. Rectangular box without a lid. Is to be made from 12 meters squared of cardboard. So basically, we're given a certain amount of material, but we want to cover the the size and the bottom of the box, but not the top, okay? We want to find the design. That gives you the maximum volume of the box. So if you want to do illustration, basically you just have a box like this. And we have front and back, left and right, and the bottom that we want to cover, but not the top, okay? And bottom. So here, let's denote the length of the box to be x, the width of the box to be y, and the height to be z. So let x, y, z be the length and height. And then, okay, so the constraint is saying the area of the box or the area of the cardboard is 12, right? So that's just we just calculate the total area without the lid. The total area without lid is, so basically we just have the bottom and the front and back and left and right, okay? So basically, the front and back is YZ, right? That's multiplied by 2, so front and back. Plus left and right, that's 2 XZ. And then we only have the bottom, that's XY. Okay, so we don't have the top. So the whole thing is 12. And so the area of the 5 sides. So this is the constraint, which is what we call equation 1. And now, so that's the constraint. Now, what do we want? We want the volume to be maximized. So basically, the volume is x, y, z, right? We need to maximize v equals to x, y, z. Okay, so we denote the v is the volume. But at the moment, we don't really have a good way to solve this kind of constraint harmonization. Basically, this is the objective that you want to maximize. Equation 1 is the constraint. Later, we will learn a method called the Lagrangian multiplier method. But here, what do? We somehow solve from equation 1 a relationship, and then we substitute into the objective. Okay. From 1, we have, so let's say we get rid of z. So from equation 1, we solve for z. Basically, what we do is we put everything about z on the left-hand side, everything without z on the right-hand side. So you have 2z times y plus z, well, x plus y plus x is the same, equals to 12 minus xy, okay? And then dividing the terms without z on the left-hand side, we will have z must be the right-hand side over the multiplier from z on the left-hand side. So we know this relationship is equivalent to equation 1. So let's just say, okay, if we have this constraint, that's the same as saying my z has to follow this rule of calculation. And then we can substitute the z into the volume. Okay, so the volume v equals to xyz can be described as a function in 2 variables. X and Y. So, and we just put down the result as follows. So basically, we have X times Y times Z, right? But Z is now the fraction value. So we just put the things together. So it's XY times 12 minus XY. Okay. So this is, so now basically Z value is defined by the fraction, but now Z is gone, right? So both the constraint, well, the constraint is satisfied, and then we just need to maximize this binomial function. Okay? Now, some other observations. By the physical nature of the problem, there should exist a dimension XYZ that yields the max value, the max volume. Such optimal design as the XYZ tuple should correspond to a local maximum of our binomial function, okay, of f of XY. So the last sentence I want to put before we conclude this today's class. Thus, it suffices to determine all local max values of our function f of XY. Okay. So basically here we replace Z by solving Z from the constraint, and we have this binomial function. Okay. And here we know we just want to look for the local maximum, local maximum point. Okay. So now we just try to solve the critical points. Here I just want to mention that this is a fractional function. So when you play with the partial derivative, you need to be careful, because here essentially we want to solve for two equations where we just have the partial derivative equal to 0. Okay, so here you want to try to factorize the expressions to the max extent. So. So here, I'm going to skip the steps, because essentially is sort of closure rule. So here we should have y squared times negative x squared plus 12 minus 2xy in the numerator, and in the denominator we have 2x plus y whole squared. And that has to set to 0. Okay. So just realize that when you're doing the partial derivative of x, this part, y over 2 is not changing. Everything else has x term, right? And then just carefully do the partial. And similarly, in terms of the partial derivative of y, it will be very symmetric. And this function is symmetric in terms of x and y. Okay? So that being said, when you interchange x and y, you still result in the same functional output. Okay, so that's what's called symmetric. With a symmetric, basically, you can check that the partial derivative with respect to y is going to be resulted from interchanging x and y in the partial derivative as well. So it's gonna be a very similar expression. But the point here is that we want to set the partials to equal to 0, okay? So although the fractional expression in the partial derivative looks kind of complicated, but then one thing we know is that we want the x, y, z values to be positive so that the dimensions are reasonable, okay? So that means these parts are not important, okay? So x and y, we don't need the 0 solutions. Okay, so x squared and y squared they're all positive in the solution that you want. And then the denominators doesn't really matter. Do not really matter. So the only thing that matters is the brackets in the numerators. Since x and y are positive that we want, we need to solve a similar system of equations, which is negative x squared plus 12 minus 2xy equals 0. Negative y squared plus 12 minus 2xy equals 0. Okay. All right, and now here we just want to solve this system of two equations and want to look for the xy pair. Okay. And also we observe that there's a common expression that's the same in both equations. So here we can observe that x squared. So if we plus both sides by x squared in the first equation, this is going to be x squared equals to 12 minus 2xy. And if you do the similar thing to the equation below, it's going to be 12 minus 2xy equals to y squared, right? So plus both sides y squared for this equation, you see, okay, 12 minus 2xy must be y squared, and also it must be x squared. That tells you x and y must have the same absolute value, right? And since here this is a conclusion. Since x and y are positive that we want, then we must have so x and y, they must have the same absolute value, and then they're not both positive, so they must be the same. And now once you know that x and y must equal, then you can utilize either one of the equations to solve for the actual value, right? So if we look at the first equation in the system, that tells you what? It tells you negative x squared plus 12. Now now y must equal to x. So this is minus 2x squared now equals to 0. And so now we have a single equation with the only variable x there. And further, well, let me write it in another line. Or equivalently, this just tells you negative 3x squared must be 12, right? So basically, if you move everything about x on the left right hand side, so basically 12 equals to 3x squared, i.e., x squared must be 4. And also, we want the positive values, so as x is positive, we have x must be 2. All right, so here we reach the only solution that is having positive xy values. So the only critical point is, so x, y, they must be equal. So x is 2, y is 2. And we are pretty much there. since a local max exists due to the physical nature of the problem, the only critical point to do has to be the local max. So we just plug in the two pair into the functions. Okay. The max volume is then b equals to f of 2, which is the function xy times 12 minus xy, whole thing over 2x plus y, evaluated at the pair 2. And so this is pretty straightforward. So basically we have 2 times 2, 12 minus 2 times 2. So basically you have 4 times 8, okay, divided by 8. So 2 times 4. So that's exactly a 4. And the unit is meter cubed. And also we should realize that this part is z, right? So this part is z. So you have what? You have 8 over 8. So that tells you z is actually 1. Okay? So basically, you have dimension here, z equals 1. So the dimension is that you have length of 2, width of 2, and height is 1 in the box. Okay. So you can see from this kind of question that when your multivariate function is complicated, and then the partial derivative may not be the challenging, but the solution of the system of equations is going to be a little bit tricky. And in the next section, we will see a little bit more complicated system. But this one is something probably not so bad. So any questions? Yes.
So are you saying that that critical point with 2 is your x and y?
Yes.
Okay.
So basically, we solve for the x value to be true from here, right? And then we also know from here that y, well, x and y must equal. So that tells you both x and y are true. So that's why we put a 2 in the pair. Okay. Any other questions? Yes.
I'm sorry, do we need to find C?
Well, if, let me see. So the question here is whether we want to find z or not. So I do recall that we want to find the design, right? We want to find the design with the maximum volume. So if they give you this kind of question, then if they only ask for the maximum volume, then we just answer is 4, right? But then the design, you have to give the x, y, z the couple. So x, well, we saw the x and y has to be 2, and z, yeah, it is 1 from that from this relationship right here. That really is up to the what the question is asking. Right. Questions? Other? Alright, now we talk about absolute and global maximum and minimums. So here, we mentioned that this is the concept from Calc 1. So here we'll give a definition. In the multivariable case, let's say we have two variables. We say the pair AB is the absolute maximum or global maximum of the function f, little f, over a set cap D if any xy pair have a functional value that's upper bounded by f of a for all xy pair in the set D. Okay, so here this brings us in. So this is the set inclusion. So the element before this notation is in the set. And similar definition applies for absolute minimum or global minimum. Right, so here we realize that for an absolute or global maximum, we needed to be the maximum output possible in the entire domain or in the entire set D. So here, somehow we want to, when we look for the absolute maximum, we want to look for the critical points, and also we want to study the boundary. That's really similar to Calc 1, where we calculate all the critical points, and we also look for the endpoints, right, of the intervals that you look at, and then we compare. Okay, so that's the exact similar steps. Okay. Computing absolute max or min of differentiable f over. Here we for the set D we restrict it to be closed and bounded. Set D. So here, when it's closed, basically it just means that it has boundaries. When we say it's bounded, it just means, okay, it's finite, okay, so it's a finite set in extent. It will not blow up. Right, so here we have the following steps. The first step is that we compute critical points of f in the set D. Okay, so basically, we look for the places at which we have zero gradients. And also we look for the points at which the function is not differentiable within the domain. And then we find extreme values, i.e. max or min on the boundary. Of that. On the boundary. Of the sets. And once we do step 1 and 2, we just compare. Okay. The largest output gives you the absolute maximum. The list output gives you the absolute minimum. And okay, so here the first step is nothing new, but the second step is kind of a necessary step. Because sometimes it's possible that you don't really have any critical point within the domain, but everything lies on the boundary. Why boundaries? So let's look at the example. Here we want to minimize function f of xy, but now the function is a linear function. It's just x plus y. So the function is simple, but here we want to define a set as a domain to be have D, which equals to all the xy pairs in the two-dimensional space. But now x is between 0 and 3, and y is between 0 and 2. So if we do the steps, we notice that okay, the function is x plus y, right? It's definitely differentiable. And then the gradient is exactly a constant vector. So the function with respect to x and y, they're both 1. So you have I plus j as the vector. So this is never 0 vector, right? So this is never 0 at any point xy. So this tells you there's no critical point. Okay, so basically we don't really have a critical point that we can get for this function. This tells you well, from the steps above, we have to look at the extreme values on the boundary. Okay? But in terms of the function itself, you see, we are minimizing this objective x plus y, right? But we know that both x and y, they must be non-negative. So that tells you, well, the logical minimum point is attained at x and y both equal to 0, right? So when both x and y are at the lower bound. So that's exactly a lower left corner of this rectangle region D, right? So that's exactly a corner point, right, on the boundary. So let's put the thing down. So however, since x and y are non-negative, x, we know x plus y is non-negative. And this equality attains at 0, 0. This is in D, okay? And this is the absolute minimum of our function. So, well, essentially, we end up with the corner point of the domain, which is on the boundary. So now let's look at a more interesting example. So here we want to find absolute max and the mean of the function f of x, y. Now this equals to a quadratic function x squared minus 2xy plus, yeah, let me put the line in the next line, with a little bit more space. X squared minus 2xy plus 2y. On the set, which is the same box. So let me cheat by copying the formula from above, but basically we just have x between 0 and 3, y between 0 and 2. So it's the same box domain, but now we just look at this quadratic function, okay? So let's just carefully do the steps. So the step 1, we look for critical points. The step 2, we look for the function behavior on the boundary. Okay, and then third, we compare, right? Step 1, compute critical points on D. So now this function is not trivial, so let's do the partials. So about with respect to x, this is 2x minus 2y. So the third term does not have y, does not have x. And then for the partial with respect to x, for the partial with respect to y, so the first term doesn't give you anything, so negative 2x plus 2. Yeah. So now we set them both to be zeros. And we realize basically the first equation tells you x must be y, right? And the second equation tells you that x must be y. So that tells you there's only one point, which is x equals 1 and y equals 1. So that's the only critical point. So the critical point here is 1, 1. And it's in the domain, right? And now step 2. So compute extreme values on the boundary of the set D. Okay. So here, let's sketch a picture for the rectangle. So basically, we have x between 0 and 3, y is between 0 and 2. So actually, we have a rectangle. So we just have the x-axis, the y-axis, the vertical line x equals 3, and the horizontal line y equals 2 as the boundaries of this rectangle, right? And then, so this is D. And then what we do is that we break it up into 4 pieces for the boundary. So basically, we have a bottom, which is what we call L1. And then vertically up, we will have what's called L2. And then at the top, we have L3. And finally, on the left-hand side, we have L4. Okay. So if we break it up into 4 pieces, then each piece is kind of simple because it's either a vertical or a horizontal line. So either the x value or the y value is fixed, right? So we break it up into 4 cases. Boundary L1, what do we have? We have, so here y value is 0, x is between 0 and 3, right? So on L1, we just plug in for f of xy, we plug in actually this is y equal to 0. X is free within the closed interval. Okay? So just recall that we let's see what the function is. So x squared minus 2xy, yeah, let me put the function down right here. So f of xy is x squared minus 2xy, right? Plus 2y. So when you plug in y equal to 0, you see only x squared is left behind. So we just need to look for the extreme values for this quadratic function on the interval from 0 to 3. Right? So this is actually pretty straightforward, but we want to write everything down systematically because we have 4 cases. Okay? Here, it suffices to compute extreme values. So let's call this function f restricted on the boundary to be g1. And this is in terms of x, so we name it g1 of x, which is x squared over the interval from 0 to 3. And we do it really systematically. So this is a univariate function. You know already this is increasing, right? But if you recall the way that we do this in the univariate case, what do we do? So it's the same thing. We do the critical point. We take the derivative equal to 0. We take the derivative and make it equal to 0. That looks for the critical points. And then here, as the interval, we only have endpoints as the boundary points, right? So basically, we have g prime or g1 prime equals to 2x, and we set it equal to 0. So this is attained at x equals 0. Okay, so this is the critical point. And then we compare, and the endpoint 0 and 3, we have g1 of 0 is 0. g1 of 3 is 9, right? And of course, the critical point is 0 itself. So here on the entire boundary, we see, okay, the minimum is 0, the maximum is 9. The minimum of f on L1 is, here we just want to put the result in the pair. So this is when x is 0, y is 0. Let's give you the 0 as the minimum. And the maximum of the function on the same boundary is now f. So x is now 3, so y is still 0. Okay, so that's the behavior on this boundary L1 at the bottom. Okay. So far so good. Right, so that's actually not complicated, right? But we just have to be systematic and do it for everyone. So let's look at one more. So now we move on to L2, right? So on boundary, so everything is really parallel. So on L2, we just we have what? We have x is 3 is fixed, and y is between 0 and 2. Right? And then, okay, function, let me move the function a little lower. So that I can see it. On L2, my function is basically I'm plugging in x equals 3 and y is 3. So we end up with what? So this is 9 minus 6y plus 2y, right? So this is 9 minus 4. And this is linear, right? And then, so this is actually a linear function. So if you want to conclude it, you can directly make the conclusion. But here, let's do this systematically. Compute. Extreme. Values of, we call it G2 in terms of y. Which is the linear function over the interval from 0 to 2. And then, of course, just keep in mind when you're doing the critical point, you take the derivative, right? But G2, taking the derivative is actually give you -4, so no critical point. So that tells you we have to just look at the endpoints. And then G2 of 0 is 9. G2 of 2 is 1 at the boundary. Of the interval. So here we just write down the conclusion, and let me cheat by copying something from a little bit earlier. So the minimum of the function on the boundary L2 is, so basically here we have x entry to be 3, only y is changing. So the minimum is attained that y equal to 2, okay? And the output here is 1. Okay? And the maximum is attained when y value is 0. The output is 9. Okay. So when we do it really systematically, it looks kind of dumb in a sense, but if you think about it as running into like a computer program that's actually a pretty solid system of steps. Okay? So the boundary L3 is going to be really similar. So I will let you guys to play with it yourself. So the minimum on the boundary L3 is f of 2, 2. So here on the boundary L3 is at the top, so y value must be a 2. But then the minimum is attained at 2. Maximum on the boundary L3 is f of 0, 2, which is a 4. And on boundary L4, which is the left-hand side edge, is also really parallel argument. And the minimum on L4 is essentially f of 0, 0. And the max on L4 is f of 0, 2, which is a 4 again. And then we can summarize all the things that we have computed. Okay? So we have on every line segment of the boundary, we have a local, we have a minimum, we have a maximum. And then we have these 8 values we compare with the critical point. Okay, so then let's insert that. Step 3. Compare values. So critical point. F of 1, 1. So we just recall that at the critical point, the output is 1. On L1, we have f of, yeah, let's put it in. This format. So f of 0, 0 is eventually a 0. F of 3, 0 is a 9. Okay. On L2, if you look above, that's actually f of 3, 2 is the minimum, which equals 1. F of 3, 0 is the maximum on L2. And L3 is what we have right above, okay? So the minimum is 2, 2, which gives you 0. The maximum here is 0, 2, which gives you 4. On L4, we have 0, 0 is the minimum, 0, 2 is the maximum. And then we just compare, right? So the minimum possible output is attained as 0. And then we have 0, 0 as the input and 2, 2 as another input, right? So we see that there are 2 absolute minimum values. Okay. And then the maximum output is attained at 9, right? The value is 9. And we have only 1. Okay, so then that's the conclusion. We conclude that the absolute maximum of f in the set D is attained at 3, 0. And the absolute max value is f of 3, 0, which equals 9. And the absolute minimum of the function f in the set D is at either 0, 0 or 2, 2 with absolute minimum value 0. So if you think about that rectangle right here, then what do we know? So 0, 0 is actually lower left corner, right? So 2, 2 is what? 2, 2 is somewhere right here. So x equal to 2, y equal to 2, right? And the maximum is attained at when x is 3, y equal to 2. So you can see that the extreme values that occur at two of the corner points and one point within the top boundary, okay? So this is kind of what happens with this function. And you see that the critical point is actually, it's where, it's 1, 1, okay? Right there, but it doesn't give you any absolute extreme point. So that's what happens within this example. So somehow you have to be careful when you're dealing with the boundaries, otherwise you cannot really attain this absolute maximum absolute minimum here. Okay? So that's what happens with this kind of question. Okay. So everything is kind of systematic. So now we do realize somehow to study this kind of absolute maximum minimum, we need to worry about the boundaries. And the thing here is that in terms of the boundary of a set of points, it's not necessarily a box. Remark. For boundaries, if we have a rectangle that we have seen from the previous example, then the boundary in this case consists of all 4 sides, not just the 4 corners. Okay? And in some situations, we may even see like a disk region. If we have a disk region, then the boundary is a circle. So that's something we have not even touched. So let's say if we have the unit disk, then the boundary is actually the unit circle. X squared plus y squared equals 1. So this is definitely beyond the context of our section right here. But basically, when we have a boundary as a circle, then you are studying the function on the circle. Okay, so that's gonna be a constraint. So this is what we're gonna study in the coming section. So which is about the constraint of the division. Okay. Now, another remark. Absolute max and mean may not always occur at critical points. It is important to study these extreme values. On the boundary. Alright, so so this is the concluding remark of this section. Okay.